About 2 minutes.
You said you were doing another lecture, is that today?
Maybe a lecture was the wrong word. I figured that the last two lectures have been a bit confusing, and just having more time where we can go over things and go through it slowly might help. And so it's more like extended office hours, if you will. And so we'll go over things on the board.
I feel like formulas and all that stuff, like it's good to see it.
Yeah.
And I feel like I'm not gonna fully like understand it until I start putting numbers to it and like really working.
Yeah, I agree. And that's kind of what the homework is supposed to help you with.
Yeah.
But yeah, I think Kalman filtering is particularly hard to understand. And even with particle filtering, I think we went through it in a confusing way. So I'll recap it today, and it's not mandatory. If anyone just has more questions, I wanted to offer more time so we could go through it. Okay, let's get started. So today we're gonna recap particle filters a little bit, and we have to cover more on how to make this practical and considerations in implementing particle filters for your homework. And then we'll touch on an idea called EKFs and then study some applications a little bit, right? So the structure of today's class is going to be, we're going to recap the basics of particle filtering. Make sure I try to explain it in a more intuitive and simple way. We'll then study these ideas of resampling, which often help a lot with particle filtering. And then we will study some practical considerations when you implement particle filters, what things might go wrong, what things you could change. And then we'll study this idea called EKFs, extended Kalman filters, and some applications. And we'll see what we can get through. But some logistics here is homework 2 is released. I think it's due on the 2nd of February. It's, I think, one of the harder homeworks, so good to start early. Because the details of filtering is often hard to get right, and it's hard to do on the robot. And so use the TAs and use their time and start early, right? Okay, and I have some extra time after this. I booked off 2:30 to 5 to just help people with understanding Kalman filtering or particle filtering if you want. No compulsion, but I'll be in, I think, gate 371, and you're welcome to drop by. And I guess we're close to the midpoint-ish. So I know some of the concepts have been confusing, and I've asked some of you for feedback, but if you feel like there's things we can do better, please let me know. We always want to make the class better. Right? And so feedback is welcome. Okay, so let's start with just a little bit of a recap of particle filtering. I'm going to do it completely on the whiteboard, just so that we can go through it slowly. Yeah. So give me 1 second. It's not showing up. Huh? Oh, there we go. Okay. Can folks see this? Right. Okay. So we're going to think about this idea of particle filtering, right? That's not good. Sorry.
Oh, I see what's happening. Let's see. Okay, popping up now. Everything good? Right. So we're gonna think about this idea of particle filtering, right? And there's three key ideas in particle filtering. The first idea is that distributions are represented by samples. So what I mean by that is like normally, let's say you have a Gaussian, right? You represent a Gaussian with a mean and a covariance, right? But when you have non-Gaussians, right, it's hard to represent them by a mean and covariance. And so when you have non-Gaussians, we're going to represent a distribution by a collection of samples, which we'll call particles, right? So let's say you have this distribution. Sorry, it's being weird here. It's represented by a collection of particles. So let's say we have like some set of samples here. You'll have like more samples here because it's higher likelihood. You'll have less samples here, some medium number of samples here and here, some lower, right? And so the point is that let's consider a distribution. Let's call it like some P of X, okay? We're going to represent P of X equivalently by a set of samples, right, and weights. Okay, and so in the simplest version of this, the weights are all 1 over n, and then you just have an unweighted set of particles. You could also consider a weighted set of particles, right? And the way to think about this is that let's say I want to know what the likelihood in a certain region is, right? So let's say I want to know the likelihood of an event in this region is, right? I sum up all the weights of the particles in that region, and that gives me a probability, right? So let's say I wanted to know what is the likelihood of an event that's in this region. You take all the particles in that region, take their weights, and you sum them up, and that gives you the likelihood, right? So what that means, there's two implications, right? The first implication is that more particles, more likelihood, right? So in regions where you have high likelihood, you'll have more particles, right? And the second is that more weight, more likelihood. So essentially there's two mechanisms to increase the likelihood. You can either have more particles in a region, or you can increase the weight of any of the particles, right? And if you want to think of this in terms of probabilities, the probability of any event happening is you take all of the particles in that region and you sum up their weights, and that gives you the probability, right? And so let's say sum of Wi times an indicator that xi belongs to some event is equal to the probability of the event. Yes. So let's take an intuitive example, right? So let's say you have your race car, right?
Can I ask a quick question?
Yeah.
As far as the weights, do you mean the more particle in a certain region means the higher weight of that region, or the individual particle might carry a higher?
So the individual particles have weights. And so there's two mechanisms to increase the likelihood. One of them is take an individual particle and increase the weight. Or you could just have more particles in that region, each with some. Okay? And so if you think of it as the probability in a region as the sum of the weights of all the particles in that region, you can increase that likelihood by either having more particles or more. Right? Both of them kind of do the same. So if you think of your race car, right? Let's say you had like a bunch of particles here, some particles here, some particles here. Let's say there are a lot of particles here. That means your like distribution is kind of like that, right? Where this is like a high likelihood, these are lower likelihood, right? And that's kind of representing your probability of where your car might be. Yes. The other thing to remember is that W is a scalar. Yeah, scalar. And X is from the state space, right? So in our race car, for instance, right, X will be X position
y position, and the theta, right? And so each particle is going to be one instance of an x position, a y position, and a theta, right? And so any distribution can be represented by this, or not any, but most distributions can be represented by this collection of particles and weights, right? And then think of probabilities, the sum of the weights of the particles corresponding to a particular event or a particular thing you want to measure. Does that make sense? Everyone following me there? So the main things to remember, distributions are represented by samples, more particles, more likelihood, more weight, more likelihood. That's it. Yeah. Okay. Anyone have any questions here? Okay. So the second thing you want to remember now, okay, is like your belief that we've talked about so far, right? Belief is the likelihood of a particular state given your measurements and your action so far is now going to be represented by a set of particles. Yes? So your belief at any point is a set of particles, and what you need to do is just figure out how to move those particles and weights around as you get more and more actions and measurements, right? That's your job as a filterer, right? As someone who does filtering. And so let's start by thinking about the dynamic step, okay? The dynamic step is giving you a P of xt plus 1 given xt and ut plus 1, right? So it's saying, okay, intuitively, we can think of this as a race car. You applied some action to it. Like it tells you like you're probably going to be here plus some noise around that space, right? So it's going to tell you how your x is going to move. So it says that if you were at x, you took u, right? Like what is your xt plus 1 going to be, right? And so, one thing that was a little bit confusing last time was trying to think about like sampling versus evaluation and this kind of thing, right? So whenever you have a probability distribution, right? This is telling you, like the probability density is telling you, how likely is a particular xt plus 1 given an xt and a ut plus 1. So you can stick in an xt plus 1, an xt, and a ut plus 1 and get a scalar, right? It tells you how likely something is. But another way of thinking about this function is that you can take in an xt and a ut plus 1, and you stick this into your dynamics model, right? And it outputs an xt plus 1. Okay. Like the simplest way to think about this is deterministic, right? So it's saying that if your state is here, you apply an action going to the right, your next state is to the right, right? Deterministic. The slightly more complicated version of this is when it's stochastic, right? So then you can say that, this function can also have some noise. So you can say xt and ut plus 1 go in, and it gives you like different xt plus 1. So every time you run it, it gives you something slightly different, right? And so what you're going to do in your homework is you have like a stochastic function where you stick in xt and ut plus 1, and you get xt plus 1, right? And so your dynamics model is something that takes in your previous state, a ut plus 1, and gives you an xt plus 1. Is that clear? So your car was here. You took an action of going to the right. The dynamics model gives you where the car is going to be at the next step, right? So the easiest case is just deterministic, like no noise. You move the car to the right by 5 centimeters. You have the previous position. The new position is 5 centimeters to the right of the previous position. When you add some noise, you're going to say, okay, you had a previous position. Your new position is 5 centimeters to the right plus some noise very quickly. And so that's what your dynamics function is. And so in Bayesian filtering, you're going to go from your belief at time step t to something which you're going to call belief bar. Okay. Yeah.
So the noise is basically like if there's some friction or something, or I guess less friction on the surface, it might go 6 centimeters instead of 5.
Exactly. So you want to maintain some uncertainty, right? Because your models are going to be wrong. And so we're going to go to this thing from what we call belief to belief bar. So belief is xt, z0 to t, u0 to t. What belief bar is going to be xt plus 1 given u0 to t plus 1, z0 to t. So note that we took another action and we're measuring the next time step. Yeah. So that's what belief bar is. Belief bar is measuring
what is the likelihood of your next time step, given that you took an action, but you did not take a measurement? The same thing we've talked about so far. And the dynamic step in a particle filter is dead easy. No complications, right? What we're going to do is we had a set of particles and weights, right? And that represented a distribution. And now you have this like dynamics function, right? And let's say you took an action in the world, right? So each of your particles and weights, or let's try to think of it as each of your particles is going to go through your dynamics function. It's going to give you an xt plus 1. And you're going to carry over the same weight. Okay. So you can think of it as x1 and ut go in to give me xt plus 1, 1, right? And you keep the same weight 1. And then you run the second particle through the dynamics model, which is x2, and ut go in, give me xt plus 1, 2, and then you keep the same weight w2, right? And so now what you've done is you've got a new set of particles, which is xt plus 1, 1 to xt plus 1 n. Each of them have been obtained by taking your previous particle x's and moving them through your dynamics model, right? And that gives you a new set of particles, but you will keep the weights exactly the same. Do not change the weights, right? So same weights, but like moved particles. Yeah, we can follow that? So we have not touched the weights, we've just moved the particles. The particles are moved by just sticking it through the dynamics function. The dynamics function can be stochastic. It doesn't need to be Gaussian. It doesn't need to be linear. So it's nice because not like the Kalman filter, it's non-linear, non-Gaussian. You just need to just do a function call with the dynamics. We're gonna follow that. So now you've moved this distribution here is belief bar of xt plus 1, right? Now you've taken your belief at your previous step, moved it forward to your belief bar. You had your race car. There were some likelihoods. You moved it forward. Now your race car is somewhere else with, some likelihoods, maybe some more noise over here. You've just moved it forward through your dynamics. So all that you do in the forward dynamic step of a particle filter is you take each of your particles, stick it forward through the dynamics model with the action. You get a new state, but you do not change the weights. Okay? Different particles, same weights. Any questions here? Okay. Make sure to ask me questions. Okay, great. And then the measurement step is more tricky, as we covered last time, but let's try to study what that means. Okay. So the measurement step is saying, okay, we've got a belief bar, right, which is the likelihood of the next state given measurement still t, but action still t plus 1. And we want to go to belief at the next time step, where belief is including the latest measurement. Right, so the difference is this extra measurement, right? So you want to include the latest measurement at zt plus 1. And that's basically it, right? Okay, so let's go back to our race car example. Now I had some belief after the dynamic step, okay? And now I'm going to shoot my little laser thing. My little laser thing is going to tell me, it's going to give me some reading, right? It's going to give me a measurement. So it's going to give me some latest measurement zt. And I know my belief is some set of particles and some set of weights, right? These weights started off with all, 1 over n, but for now, let's just keep them as abstract weights, okay? So what I want to do is figure out, okay, I've got some measurements. How do I incorporate this into the set of particles to better represent this belief, which incorporates the latest measurement, okay? So the idea is that for particles, you can measure what is the likelihood of the measurement being produced by a particular state. So you have this measurement function where you can stick in an xt. You can stick in a zt and you can get a number saying how likely it's going to be, right? So you can almost think of it as like a function. Let's call this measurement. It's going to take in an xt or a zt, and it's going to give you a scalar, right? Higher the scalar, more likely. Lower the scalar, less likely. And so now how do we make this particle set better represent the belief after using the measurement, right? One way is you can try moving the particles around, right? So in the dynamic step, we said, okay, well, probably like the dynamic step was said move this way, so we moved the particles, but we didn't change the weights, right? And now we've said, okay, we've got some measurements. The measurements are, you can take the measurement function, stick in each of these and get a number for them, right? So we just say, how likely was it that that state produced the measurement that you actually got? Now, one option is that you can move the particles around, but that's kind of difficult. You don't know where to move them to. The easier option here is that you can say, okay, we have this number, we've stuck in xt plus 1 and zt plus 1, right? So I think I got some notation wrong here, but you got zt plus 1, not zt, sorry. And so you can stick in zt plus 1 and xt plus 1 for some I into this like measurement function. It gives you like a scalar, right? And then what you can do with the scalar is you can go and change the weights, right? So we said there's two ways to change the probability distribution: increase the number of particles, so move the particles around, or you can change the weights, right? And so all you're going to do in the measurement step is you're going to take the scalar that you get, right? You stuck in the actual measurement that you got, and then each of the particles that you have right now, you're going to stick into this function. It's going to give you a scalar, and then you're going to readjust the weights according to that scalar, right? And so what you'll get is you'll get a p of zt plus 1 given xt plus 1, 1, a p of zt plus 1 given xt plus 1, 2, all the way till p of zt plus 1 given xt plus 1 n, right? You have n scalars. Just normalize them, right? So let's call eta the sum of these, right? And so you can normalize them to say you're going to get pzt plus 1 given xt plus 1, 1 by eta plus pzt plus 1 given xt plus 1, 2 by eta. Or rather, this is the weight for particle 1, this particle 2, all the way till particle n, right? And so all you're going to do is take the previous weights that you have and then multiply them by this number, right? Intuitively, you can think of it this way. The numbers that are higher, the weights will increase. Numbers that are lower, the weights will decrease, right? So for instance, if you go back to our race car, it's pretty unlikely. Let's say I got a measurement of like 2 centimeters, okay? It's pretty unlikely that if the race car was here, it would produce a measurement of 2 centimeters, right? So these numbers are going to be much lower than these numbers. And so what's going to happen is that these numbers, these weights of these particles will go way down, and the weights of these particles will be high, right? And so what you're going to do is you're going to say each weight gets multiplied by this number, and now you have a new set of weights for the same set of particles, right? So you've said, okay, we have the same set of particles, and now you've got a new set of weights. And that's going to be your belief at the next time step. Okay. So let's make sure we understand that correctly. In the dynamic step, we've moved the particles, we have not changed the weights. The measurement step, you don't know how to move the particles, you keep the particles the same, but just change the weights. And the way you change the weights is you stick in your actual measurement and each particle state into this measurement function. It gives you a scalar. You normalize the scalar and multiply each of the weights. And so now you have a new set of weights for the same set of particles, right? So you can think of it as dynamic step moves the particles, keeps the weights the same. Measurement step moves the weights, keeps the particles the same. Repeat, repeat, repeat. Is that clear? Okay. Go ahead.
So basically, the first step, you're gonna get all of your weights and states and everything. And then once it moves, you're taking a measurement and changing everything moving here to here and then doing it again. Right?
So you started with some set of particles and weights. In the dynamic step, you don't change the weights.
Yeah.
You just move the particles. Move, right? And then the measurement step, you take a measurement and then you keep the particles the same, you just change the weights. And then you go back to the dynamic step.
Here, not over here.
Exactly. Because we know that the probability is a combination of both where the particles are, because number of particles, and the weights of the particles, right? So there are just two different mechanisms to change probability. One of them is moving the particles, one of them is changing the weights of the particles. How do we feel about that? Yeah. That's same as the model. Yeah. Well, you like sample from it. So you like take in an XT and a UT, you stick it to the dynamic model and you return one sample. Just like one random sample. Yeah.
This way is not in each step, right? Because the weights are gonna be different in each step. So it's fully dependent on ten steps.
Well, you're still using the Markov probability.
So it's
As in-
still, you need the last.
You need the last step.
So
You don't need.
independent
Correct.
of
Yeah,
all the
same.
other steps.
Exactly. Okay. So that's all the particle filters. You just started with a set of particles and weights, dynamics moves the particles, measurements moves the weights, you repeat. And now, okay, what do you do with this thing, right? Now, finally, let's say you wanted to compute something like the average cost under, or let's say you want to compute the average position, right? The way you're going to compute the average position is you're going to say, like, the average position is basically the expectation under the belief of xt, right? It's looking for the average position. All you're going to do is you're going to take in the sum of wi xi and sum it up from 1 to n, right? And so whenever you want to take the average, just take the weighted sum of x. You can replace x by any f of x, and you take the weighted sum of f of x, and you can take any number of expectations that you want, right? With these samples. So let's say you wanted to get the average position or the average cost or anything like that. You take each of these particles, treat it as the truth, right? Get what the function is going to be, and then take the weighted sum of those over each of, like, over the whole set of particles. And that's going to be how you use this probability. We haven't talked about how to use it yet. That'll be from Friday onwards, but that's the key idea. How do we feel about that? Okay, more clear than last time? Good. Cool. So we can go off the whiteboard. Let's see. Sorry. Okay, so we're back here. The particle filter algorithm is exactly what I said. You know, sample your particles from your dynamics weights, from dynamics function, propagating the weights, weight your samples, normalize, don't move the particles, just change the weights, you repeat, right? Particle filter algorithm. So that's the basic algorithm. It's not going to be what works. So let's try and understand what happens across multiple steps, right? So across multiple steps, you know, in the dynamic step, you move the particles. In the measurement step, you change the weights. Like, let's consider the size of the size of these circles to be the weights, right? You change the weights, and you're going to repeat this over and over and over, which means that the particles are going to move and the weights are going to get multiplied every single time, right? So what are some issues that could happen? Yeah. Some of the particles might be too big, so there's numerical issues, right? So some of the particles blow up. Or you have numerical issues of too big or too small, right? You start losing things numerically. What's another issue that could happen? This one's a little more subtle, maybe I'll tell you guys. Basically, the particles only move in the dynamic step. So imagine that you like ended up in a situation where there was like a lot of particles in the low likelihood region. Like the particles only move from the dynamic step. So a lot of particles will get stuck in some region and the weights will change, but the particles may get stuck. Right. So imagine that you had like particles are, let's say your dynamics model, when you're in this like low likelihood region, keeps the particles there. Because the particles are only moving because of dynamics. If the dynamics model doesn't move the particles, you have a lot of wasted particles stuck in one region, right? And so you may actually really care about this region, but you may have a lot of particles with low weight stuck in one region. So you're wasting a lot of your particles in the wrong region of space, right? And so what happens then is you have like 1 million particles, but like 500,000 of them are sitting in this like low likelihood region. And so your effective number of particles is not that big because they're like getting stuck in certain regions of space. And so like imagine your dynamics model was like here by the wall and you keep banging into the wall and you don't move, right? like your particles get stuck there and they don't move. And so that's, you often have this like particle deprivation issues, where particles start like not being useful. Right? And so then your memory blows up and the numerics blow up and it's not great, right? Okay, so the issue is that the motion model is or the dynamics model is the only thing that moves the location of the particles. And the measurement model is fine, but it only changes the weights. It doesn't move the particles. That's not what it is. So we're going to propose a simple solution, which is resampling, right? And resampling is pretty simple idea. Resampling is just saying, let's say you had a set of weighted samples, right? So you had X1 to Xn with weights W1 to Wn. What you're going to do is you're going to try and return a set of unweighted samples, right? So you started with, let's see, maybe I can write this out here. Okay, so you started with X1 to Xn and W1 to Wn. What you want to end up with, and these weights are not all, uniform. What you want to end up with is a new set of particles, X1 to Xn, where the weights are all uniform again, right? The weights are all 1. And so, or 1 over n. And so what resampling says is that given a distribution of non-uniform weights, how do we generate a set of unweighted particles that represents the same thing? So what I said earlier was, okay, a probability distribution can either be defined by the weights or by the number of particles in the region, right? And so what this is going to say is that for regions that have, let's say, high weight, you replace it by more particles in that region. So if we're having this issue of particle deprivation in like shitty parts of space, what this is saying is that if we do resampling, the particles get moved to the parts of the space that are higher. Right? And so we're saying we want to go from a weighted set of particles to an unweighted set of particles that represent the same thing. Yeah. And so in doing that, your particles are going to the parts of space that you care about, that matter. Yes? Okay. So we'll look at that, but really we want to figure out this procedure, which is going to allow us to do this n different times so that we can get a whole set, right? And the strategy we're going to use to do it is super simple. It's just, spinning a roulette wheel, random sampling, right? So we're going to say, well, let's make a roulette wheel like the arc length corresponds to the weights, right? So things that have higher weights have higher arc length. Things that have lower weights have lower arc length, and then you're going to just spin the roulette wheel randomly, right? And so the chance of it landing on something which has high weight is higher, obviously, and the thing that chance that it lands on the lower weight is lower, right? And so you construct this roulette wheel and then you spin it over and over and over, yeah? And so you're just going to keep spinning it. It's going to keep giving you different samples, and that's going to give you your like new unweighted distribution, right? And so the intuition here is that you're going to construct this roulette wheel, but the width of the areas are going to be dependent on the weights, right? So bigger weights, more area. So the chance of landing on them is higher, right? And so you keep resampling it, you're more likely to get samples in these regions, right? So you replace the weights by just more samples, but everything's unweighted again. And so you can also kind of do this on a line. You don't have to do this on a wheel, right? Let's say you had 3 particles, you can take their weights, normalize them until they add up to 1. And then you can just choose some random numbers, right? So you just choose a random number. 0.97 will be here. 0.26 will probably be here. And 0.72 will probably be here. Right? Am I getting that right? I guess so I think 0.26 and 0.72 will be here. And then 0.97 will be here, right? And so you can construct, basically you can take your normalized weights, run a random number generator to resample. All you need to do is see which one of the buckets it falls into, right? So what we've done is we've converted we had 3 particles earlier, which were weighted. Now we're going to get 3 more particles, but they're unweighted, right? And so, but the 3 particles we'll get is that there'll be 2 particles here and 1 particle. Okay. Does that make sense? Get rid of those samples because the old samples are weighted, and so you want to just keep the new samples. Okay, so why might this be bad? Or okay, maybe let's start with why might this be good. Like, what will this help with, right? Yeah. Right. Exactly, right? So samples that are stuck in the region, earlier we were only moving them according to the dynamics model. Now we're able to move them according to resampling too, right? And why might this be that?
Get unlucky and end up with a bunch of stuff there.
Yes, you got unlucky and you end up with a bunch of samples, which is really a problem of variance, right? If you had infinite samples and infinite resampling, this would not be a problem. It's like when you have finite samples and a finite number of rolls, you can get unlucky, and when you're unlucky, you can get screwed, right? And so you have to be a little careful here. But the way we're going to do resampling in our particle filter is we're just going to have our weights, right? At any point of time, we're going to have, ignore the equations, just think of them as like a set of X's, a set of W's. We're going to put them on our roulette wheel or our line, sample a bunch of times, we're going to get a new set of X's. That's it, right? And note that the X's are not going to be like wildly new X's in the middle of space. They're still going to correspond to some of the particles that were in the set, right? It's not like we constructed a magical new particle. It's still amongst the particles that we had. So for instance, if we had, x1 to xn, and then we had x1 prime to xn prime, our new particles, like these ones will be one of these. Each one of these will be one of these, right? But you'll just have more particles in the regions that have like higher weight. Right? They're not going to magically, like if you notice what I did here, like these are not magically in the middle of space. They're in one of the positions of the other particles, right? And so when you do resampling, it's almost like you redistribute the particles in those regions, but you set everything to be unweighted. And things that have higher weights will have more particles, and things that have lower weights will have less particles.
So effectively, you're just kind of reclustering the particles
Correct.
in the spot that you're, where that
Right.
probability says more likely.
And so you're just switching these two modes out of weight versus number of particles. Okay? And so you're swapping out weights for more particles.
What if you do get unlucky and end up at weight one there, where it's very unlikely that that's where it's at? Are you now clustering into that?
Yeah.
That spot?
But the hope is that if you have enough particles, that happens with low.
So you said all of the same number of particles that you started with, so you have the same.
Yeah, you could increase the particles. There's nothing that stops you from doing this. But then you like incur extra number. Yeah. And so there's no reason to not sample more particles. They just need to be like there has to be a trade-off with navigating. Okay. Yeah, there will be a bunch of identical samples which you can resample. Yeah. So the particle diversity can collapse. Yes. So one of the practical issues that comes up, we'll talk about it, is that the particle diversity, if you like do too much resampling, your particle diversity can collapse to like certain regions. And so there's a few strategies that work. One is don't resample all the time, just resample sometimes. And two is just like add in more particles. Just like introduce new particles. Just like that. Okay, so we've talked about going from a set of particles to let's say we had a set of weighted particles. We want to go back to a set of unweighted particles, right? So we're going to construct our line, we're going to sample, and now our random numbers tell us that we have two of them where particle 2 was, and one of them where particle 3 was, right? And so our new belief distribution is going to have 2 particles in that region and 1 particle in the region, right? So then you didn't manufacture something, but you like move the particles to regions that were more promising, better, more likely, right? And these are like not issues if you have infinite samples and infinite sampling and infinite particles. It's only in the finite sample case that it becomes a problem. Okay, so how does this work in practice? This is actually from one of Dieter's experiments, I think from the 90s or late 90s, early 2000s, but they're trying to like navigate around a museum. But you can see that initially the particles are all over the place, right? Then you send out your laser beam, it changes the weights and where the particles are. You have a better idea, send out again, you localize where particles are more accurately.
send out again, your particles are now more accurate, right? And so you've got a pretty, like,
you've got a pretty accurate sense of where your robot might be. And now, of course, this is affected by how accurate your measurement model is, right? Because if your measurement model is pretty noisy, then your weights are going to be not that accurate. If your motion model is pretty noisy, you spread things out more. So the same issues that we had the Kalman filter are going to be issues here, right? But at least it's not linear and it's not Gaussian.
So if your model is correct, I mean, what is the likelihood that you're gonna be exactly where you think you are? Like, is it like within a foot or so, like with the race cars exactly, like, would it be like you're within a foot of where you think you are, or you're?
Less than that, like a couple centimeters,
Oh, okay, so it's like, yeah, spot on.
pretty small. Yeah.
Okay.
because you want to like navigate around obstacles and stuff, right? It has to be less than that, yeah.
Yeah, yeah.
Right, so those particles get really low. Right, because like the likelihood you got that reading from that particle is extremely low. Now, the one issue that's going to happen is you have like symmetric maps, this can become a problem with more than one particle. But if you had an asymmetric map like that here, like the point is the laser only reaches some regions. So it's extremely unlikely you get that reading from particles way over.
Right. So, okay. So this was our original set of particles.
We send out the lasers, okay? Right, so then our lasers tell us, okay, what is the likelihood that that laser scan pattern was found by each of these different points, right? Now, obviously, these points will be lower than the points up there, so these points will get weighted down. And those other points will get weighted up, and with resampling, we basically start killing particles in the bad regions of the space, right? And so then you start seeing that the particles go more towards likely regions of the space, right? But because the scan is not like perfect, it's not unique necessarily, right?
It's not going to instantly collapse to a single particle. Right, right. No, it's not about that. It's not about near the laser.
Like the position of the laser is not the problem. The question is like, how likely is a particular position to generate the particular pattern of laser scans that you get? Right? So imagine that your robot was here. Right? You got some pattern of laser scans from like your current measurement. If your robot was here, it's very unlikely to produce that pattern of laser scans. So it's not about being close to the laser or not. It's about whether you would get that pattern of laser scans over here. And it's unlikely that you would. Right? And so like, I think it's a mistake to think about it in terms of like distance from the laser scan. Try to think about it as how likely is each state to produce the measurement that you actually saw. Does that make sense? Because it's not unique, right? So like plausibly, like a position here could have generated those things that were. So like imagine you set your robot here, send out a laser scan. Like those measurements and the measurements up there are not that different. Right, so it's not about the position of the laser scan, it's about the pattern of like laser readings that you get. Right, so it's like imagine I shot out something and I like received a pattern. And everything is just like trying to see how likely was it that the pattern was produced if I was in each of these positions, right? And the point is that over here, there's some likelihood that that pattern would have been produced because there's like some symmetries in your space, right? And so that's why your likelihood doesn't collapse there. Does that make sense?
All right. So we'll kind of skip this, but so that's resampling in particle filters, right? Just moving particles around. Now, one of the issues that we just talked about is that if you get unlucky, like imagine that you had 6 particles, right? 3 particles in each room, and you just resample. Right? If you get unlucky, you will end up with all the particles in one room, right? And if you end up with all the particles in one room, even if there's no motion, if you just keep resampling, there's some likelihood of things moving, right? And then you get this like particle collapse. Right? So if you sample too much, then you get particle collapse. And
essentially you can work out the math here, but if you just like IIP resample where each of these particles should be, there's some likelihood that all the particles will end up in one group. Right, and that's kind of not what you want. You want, like, ideally, you'd like that the more you resample, like the belief remains the same. And if you have an infinite number of particles, that would happen. If you have a finite number of particles, you can get unlucky. And so the solution is the dumbest possible solution. Don't sample so much. So try to figure out when this kind of oversampling might happen, right? While the weights are equal, if the weights are high entropy, in these kinds of scenarios, don't oversample, right? Because oversampling can lead to this like unlucky getting stuck in certain regions. So that's the first issue, right? So in your homework, if you're ever finding that your particles collapse, maybe you're resampling too much, just like cool it on the resampling, yeah? And then the second issue is that, you keep spinning the roulette wheel, you're doing it independently. And, we talked about, we can get unlucky, it's high variance, right? And so you might not sample the right set of particles because of these unlucky trials. And so they came up with a kind of clever way of doing low variance resampling. And the idea is like, imagine that on your roulette wheel, right? Rather than picking like one point, imagine that, let's say you want to sample n particles. Okay? You're going to make a device which has n spokes equally spaced. And you can almost think of it like, let's take our roulette wheel, right? And then like make a device which has n things equally spaced. Okay, you want to resample n times, and then you're going to spin that n spoked device, right? And so what's going to happen is that it's still random where it ends, right? But then each of the particles is spaced out equally after that. And the intuition here is that even if things are spaced out equally, the things that are high likelihood will still have more particles. But because you're sampling all the particles at once, it's lower variance and you have less chance of like just missing particles because of unlikely bad luck. And so this is an idea called stochastic universal sampling, right? And so all you're going to do is, let's say you chose a random number, you wanted to generate m samples, right? You're going to say r plus 1 over m, r plus 2 over m, r plus 3 over m, and you're going to just have like, you can almost think of it as like, you will generate m samples all at once, right? And that's going to be a lower variance way of generating. The exact math of this is a little more involved, but just think of it as like a trick to sample more efficient, right? You just want to say, almost think of it as like you have like, whether it's a roulette wheel or line, doesn't matter. Even if you have like a K-prong device that you like move around, the random number shifts it, but you like sample all of them at once. And so that's a trick that you want to use in your homework. You want to make sure that you're not oversampling, right? So you want to make sure that you do those two things. And the other practical concerns are maybe a little less important, but we'll cover them in our paper presentations on Wednesday, right? So in your localization project, you're going to implement the kinematic model for the car that we talked about last week. You're going to implement a laser beam sensor model, right? That's a motion and sensor model, and you're going to implement the particle filter. So the car model is nonlinear, and you want to not deal with the Kalman filter bullshit. So you're just going to deal with the particle filter. It's going to be easy. You just need to combine your motion sensor model, just using the stuff we discussed today, right? Do it with resampling, do it with like this low variance resampling technique. Be careful on how much you resample and so on. Yeah, try those things. Robotics doesn't work in the first shot, so don't be frustrated. Keep trying it. It'll eventually work. Sometimes you need to tune some parameters, like how many particles you have, where's your initialization, how much noise you're adding. You might want to add in more particles sometimes. Like you have to play around with these things to get it to work.
There's tests, right?
Yeah, there are tests. Right. So yeah, don't get frustrated. It'll take some time. Ask on EdSTEM and come to office hours. I think those things will help. Let's skip EKF, but just really quickly, I want to show you some history on filtering, which I thought was cool. So I was looking up like where did Kalman filters and stuff come from, and it seems like the Air Force actually funded a lot of this research for like driving planes and helicopters and stuff around. And so they funded Kalman when he was developing a bunch of this stuff. And so you might want to look into the history, but it's pretty much used in almost every government defense system, on your Mars rovers and on your planes and on your helicopters and your aircraft carriers. And so I think that's pretty cool. Yeah, I guess just to kind of like wrap up what we studied in the first section of this class, we are studying this topic of Bayesian filtering, which is figuring out where you are from your measurements, right? And Bayesian filtering is basically just applying a recursive Bayesian updates, just applying Bayes rule over and over and over, right? And so the basic idea of Bayesian filtering, you start with the belief, you run a prediction step, you run a measurement step, prediction, measurement, prediction, measurement, prediction, right? That's the basic formula. We instantiated 3 different ways. Well, we didn't actually cover this, but that's okay. We have linear Gaussian, which we talked about with the Kalman filter. So if the dynamics model and the measurement model are linear and Gaussian, that's the Kalman filter. If it's non-linear and Gaussian, you have this thing called the extended Kalman filter. You can go through my notes. They have some of that. And if it's non-linear and non-Gaussian, then you want to use the point. And the idea here is that it's not just useful for finding out where you are, it's also useful for problems like SLAM, which is like figuring out both the map and where you are. So I thought this video is kind of cool. So they're driving around, an underground garage and both mapping the environment and figuring out where you are together, right? So you can model that as a different kind of filtering problem, where you're trying to estimate both the map and the position, right? So in your homework, you're going to estimate only the position, but you can also estimate the map. It's just another variable. And so these filtering ideas are super powerful. They're even used in deep learning. And so I think, yeah, you want to maybe read up on SLAM. We posted some readings, and I think that'll be a fun exercise. Product placement by roboception. One thing is, I sent out an email about presenting on Wednesday. Are people here presenting? Some of you are presenting? Okay, so come talk to me if you're not sure on what we have to do, but basically just tell us about what the paper is, tell us the premise, tell us the results, tell us what you thought is cool, not cool. Let's have a discussion. And on Wednesday, I'll post something on EdSTEM where you all can comment, and like it'll be due next Monday. So. Okay, see you all Wednesday. Thank you.
Do you want us to go on the paper? Like, are we doing